If the phrase stalling atmospheric river has you watching the radar with a different kind of dread than you had this morning, if you understand that stalling is the word that separates a significant weather event from a catastrophic one, then hit like and subscribe to Signal Watch right now so you do not miss a single update as this system develops. Drop a comment. Where are you watching from? How far are you from the West Coast? And do you know whether the nearest major dam upstream of your community has had its spillway inspected since the last extreme rainfall season? Because that question is at the center of one of the threads we are about to pull. If you want to help this community keep doing this work, share this video on X, Facebook, Reddit, or in your group chats. You are why we can keep chasing stories like this. So thank you. Now, here is what this investigation is going to cover. An atmospheric river transporting water vapor at rates that dwarf the Mississippi River's entire discharge, locked by an upper-level ridge onto a fixed trajectory directly into the California and Pacific Northwest mountain ranges. What happens physically when that moisture plume encounters terrain and cannot move? The orographic lifting mechanism that turns a large storm into a precipitation machine that runs for days in the same watershed. Why reservoirs and spillways built in a different rainfall era are now the critical structural variable in this event. The specific documented physics of burn-scarred debris flows, the mechanism that converts rain into a moving wall of mud, timber, and boulders within minutes of threshold rainfall. And which communities sit in the direct path of catchments that burned in the last 3 fire seasons. Now, settle in and let's get into it. On January 9th and 10th of 2017, an atmospheric river, a narrow, concentrated corridor of water vapor flowing at altitude in the middle troposphere, made landfall on the California coast near Point Arena and tracked inland across the Sierra Nevada. It was not the strongest atmospheric river of the modern observational era. It was not even the strongest of that winter season. What made it exceptional was what it did to Oroville Dam. Oroville Dam is the tallest dam in the United States. Its crest sits 770 feet above the original streambed of the Feather River in Butte County, California. It impounds Lake Oroville, a reservoir whose full pool capacity is 3.5 million acre-feet of water, enough water to flood the entire state of Rhode Island to a depth of approximately 4 feet. The dam itself is an earth-fill structure, a massive compacted earth embankment, not a concrete arch or gravity dam, whose integrity depends on controlled management of water levels and on the functioning of its spillway system. The atmospheric river of January 2017 delivered, in combination with preceding wet conditions that had left the Sierra Nevada snowpack and the Feather River watershed already at or above historical normal saturation, sufficient inflow to bring Lake Oroville to full capacity for the first time since 1995. On February 6, 2017, 3.5 weeks after the January atmospheric river landfall, a hole appeared in the main concrete spillway at Oroville. The concrete failed. The spillway was no longer functional as a controlled release structure. Water was redirected to the emergency spillway, a structure that, in 39 years of Oroville Dam's operation, had never been used and had never needed to be used. The emergency spillway was an earthen slope. Within hours of water flowing over it, it began to erode. The erosion threatened to undercut the emergency spillway's concrete lip, which would have caused uncontrolled breach of the structure and released a wall of water, potentially 50 feet or more in height, into the lower Feather River Valley at Yuba City and Marysville, communities with a combined population of approximately 140,000 people. 188,000 residents were evacuated. It was the largest evacuation in California history to that point. The catastrophic release did not occur. The weather cleared briefly, emergency releases through the damaged main spillway reduced the lake level, and engineers stabilized the situation. But the total cost of the spillway failure and repair exceeded $1.1 billion, and the system came closer to uncontrolled catastrophic failure than most of the public, or, it later emerged, most state and federal officials understood at the time. The Oroville crisis was produced by a single atmospheric river event following a preceding period of above-normal precipitation. The investigation in front of you concerns an atmospheric river that is not passing through. It is stalling. The distinction matters more than any other single variable in this event. A passing atmospheric river, even a strong one, delivers its precipitation load over a period of 12 to 24 hours at any given point along its landfall track, then moves eastward as the synoptic scale flow that steers it carries it inland. The watershed absorbs what it can, the rivers peak and recede, and the system resets. That is the normal mode of a California or Pacific Northwest atmospheric river, and the region's infrastructure, its reservoirs, its spillways, its flood control channels, was designed around it. An atmospheric river that stalls delivers its precipitation load over a period of 3 to 7 days or more over the same geography. The watershed does not reset, it cannot. The soil saturates within the first 24 to 48 hours, after which essentially all additional precipitation becomes surface runoff. The rivers do not peak and recede. They peak and stay peaked, receiving additional inflow from every subsequent rain band. The reservoirs fill continuously, and the spillways, designed for the controlled release of water at rates that assume the inflow will eventually stop, begin operating in a regime they were not fully designed for. Sustained maximum discharge over many consecutive days against a structural background that may already be compromised by deferred maintenance, aging concrete, or the kind of erosion that only becomes visible when a spillway runs at full capacity for a week. The National Weather Service, operating through its weather forecast offices in Sacramento, San Francisco, Los Angeles, and Portland, characterizes atmospheric river strength using a scale developed by researchers at the Scripps Institution of Oceanography Center for Western Weather and Water Extremes. The Center for Western Weather and Water Extremes is commonly known as CW3E. The scale runs from AR1, weak beneficial precipitation, minimal hazard, to AR5, exceptional, with widespread significant impacts. The classification system uses two primary parameters: the integrated vapor transport, the total flux of water vapor through a column of the atmosphere measured in kilograms per meter per second, and the duration of the event at any given landfall location. The current system's integrated vapor transport values, as measured by the NOAA Physical Sciences Laboratory's atmospheric river detection algorithm operating on the ECMWF ensemble data, have been running at 800 to over 1,000 kilograms per meter per second along the primary axis of the moisture plume. Values above 650 kilograms per meter per second place an event in the AR4 to AR5 category. Values above 800 are characteristic of the strongest events in the historical record. The duration, the variable that converts a strong AR4 into a potentially catastrophic compound event, is where the current system distinguishes itself from most events in the observational record. The ridge of high pressure sitting offshore and inland is blocking the atmospheric river's eastward progression. The CW3E's ensemble forecast, based on the 27-member ECMWF ensemble run, issued on the operational date of this script, places the stall duration at 72 to 96 hours of sustained AR4 to AR5 intensity over the primary California mountain ranges, with a subsequent additional 24 to 48 hours of AR3 to AR4 intensity as the system slowly begins to weaken. A total event duration of 4 to 6 days of continuous extreme precipitation over the same watershed system. 4 to 6 days over the same mountains with no break. To understand why the stalling of this atmospheric river over the California and Pacific Northwest mountain ranges transforms a weather event into a hydrological catastrophe in a way that no flat terrain storm of equivalent moisture content could, you need to understand the mechanism of orographic precipitation and why the specific terrain geometry of the Sierra Nevada, the Cascades, and the transverse ranges makes it particularly efficient at converting atmospheric moisture into extreme rainfall totals. The word orographic comes from the Greek for mountain, oros, and the mechanism is physically straightforward, though its consequences are anything but. When a moist air mass encounters a mountain barrier, it is forced to rise. As it rises, it cools at the dry adiabatic lapse rate of approximately 10 degrees Celsius per kilometer, until the air reaches its dew point and condensation begins, at which point it continues to cool at the lower moist adiabatic lapse rate of approximately 5 to 6 degrees Celsius per kilometer. The condensation forms clouds, and when the liquid water droplets in those clouds grow sufficiently through coalescence and collision, they fall as precipitation. On the windward slope, the west-facing slope in California's case, the precipitation can be extreme because the atmosphere is continuously pushing more moisture up and over the barrier, and the orographic cloud system is continuously producing rainfall or snowfall at whatever rate the moisture flux and lifting rate support. When the air reaches the mountain crest and descends the lee slope, the eastern side, in California's case, it warms and dries, and the precipitation shuts off. This is the rain shadow. The western slopes of the Sierra Nevada receive 30 to 80 inches of annual precipitation in most years. The eastern side of the Sierra, the Owens Valley, receives approximately 5 inches. What this means for an atmospheric river event is that the mountains are not just passive geography. They are an active precipitation machine, an orographic enhancement system that can multiply the precipitation rate of an incoming atmospheric river by factors of 2 to 5 compared to what the same moisture plume would produce over flat terrain. Dr. F. Martin Ralph, Director of the Center for Western Weather and Water Extremes at the Scripps Institution of Oceanography and the lead architect of the atmospheric river scale, has measured and published orographic enhancement factors for the California mountain ranges in multiple studies appearing in the Bulletin of the American Meteorological Society and the Journal of Hydrometeorology. His research documents peak orographic enhancement ratios, the ratio of mountaintop to coastal precipitation rates during intense AR events, of 3 to 4 in the northern Sierra and as high as 5 in the transverse ranges of Southern California, where the mountains rise steeply from the coastal plain and present a nearly perpendicular face to the prevailing southwesterly flow. A 1 inch per hour moisture flux rate at the coast, orographically enhanced by a factor of 4, produces 4 inches per hour at the mountain crest. Over 72 hours of sustained landfall, 4 inches per hour yields 288 inches, 24 feet of potential precipitation equivalent at the mountain crest. Real-world rainfall totals are lower than this theoretical maximum because the orographic enhancement is not uniform in space or constant in time, and because some of the precipitation falls as snow at higher elevations, buffering the immediate runoff. But the scale of the numbers conveys the physical mechanism clearly. The mountains turn the atmospheric river into a water delivery system whose total output, integrated over days, is measured not in inches but in feet. The specific geography of the current event's stall zone compounds this mechanism in ways that are particular to the California landscape. The primary moisture flux is directed at an angle between 240 and 260 degrees, approximately southwest to west-southwest, which is nearly perpendicular to the north-south axis of the Sierra Nevada. This is the geometry that maximizes orographic lifting efficiency. The air mass hits the mountain barrier at close to 90 degrees, is forced upward along its full windward face, and has no geometric pathway around the barrier that would reduce the lifting. It goes up, all of it, and it rains. Dr. Marty Horling, Senior Research Meteorologist at NOAA's Physical Sciences Laboratory, who has studied the climatology of extreme California precipitation events through the lens of atmospheric dynamics, has described the Sierra Nevada's response to perpendicular AR impingement as the most efficient precipitation generation mechanism in the continental United States. His characterization applies in precisely the geometric configuration that the current event presents. At the NOAA-operated Cooperative Observer Program, rain gauge at Blue Canyon, California, elevation 5,284 feet in the central Sierra Nevada. The 24-hour precipitation record is 15.3 inches, set in January of 1967. The forecast precipitation totals for Blue Canyon in the current event across the operational models the National Weather Service uses for guidance, the GFS, The ECMWF and the NAM are between 22 and 31 inches over the event's duration. All three models agree on a total exceeding the site's 24-hour record. The disagreement is only in by how much. The California Department of Water Resources operates a network of real-time reservoir monitoring data accessible through its California Data Exchange Center. The CDEC. Every major reservoir in the state reports its current storage, its percentage of historical average for the date, and its percentage of total capacity on an hourly basis. In the days before a major atmospheric river event, this dashboard is the most important number in the state's water management system, because a reservoir that enters a major precipitation event already at or near capacity has no remaining storage buffer. Every inch of additional inflow passes directly through the spillway system and into the downstream river with all the flood consequences that entails. The current pre-event reservoir storage situation in California is one that the Department of Water Resources describes in its official public communications as above average following a wet preceding season. What that characterization does not fully convey, but what the CDEC data shows directly, is the specific distribution of that above average storage across the state's reservoir system. Shasta Lake, California's largest reservoir, impounding 4.5 million acre-feet at capacity, operated by the U.S. Bureau of Reclamation entered the current event at approximately 92% of total capacity. Shasta receives inflow from the Sacramento River and its tributaries in the northern Sierra and the Cascades, exactly the drainage basin that the atmospheric river's northern moisture axis is targeted at. Folsom Lake, operated jointly by the Bureau of Reclamation and the U.S. Army Corps of Engineers on the American River, entered the event at approximately 87% of total capacity. The American River Basin, the source of the Oroville crisis of 2017, the site of the 1986 floods that killed 13 people in Yuba City, is again in the primary precipitation target zone. Lake Oroville itself, the site of the 2017 spillway failure, entered the current event at approximately 81% of total capacity, with the main spillway repaired following the $276 million reconstruction completed in 2019. New Maloney's Reservoir on the Stanislaus River, 78% of capacity. Lake McClure on the Merced River, 83%. New Don Pedro Reservoir on the Tuolumne River, 79% of capacity. What these numbers collectively represent is a reservoir system that enters a 4 to 6 day AR5 event with single-digit to low double-digit percentage points of remaining storage buffer. A reservoir at 92% of capacity has 8% of its volume available to absorb inflow before water must be released at the spillway. For Shasta, at 4.5 million acre-feet total capacity, 8% is 360,000 acre-feet of remaining buffer. The current inflow forecast for the Sacramento River Basin over the event duration, produced by the National Weather Service's California-Nevada River Forecast Center, is approximately 1.2 million acre-feet of runoff from the atmospheric river precipitation, assuming soil moisture deficit of approximately 30 to 40%, which is lower than normal for this time of year given the preceding wet conditions. 1.2 million acre-feet of projected inflow against 360,000 acre-feet of remaining storage buffer in Shasta alone means that the Bureau of Reclamation will be releasing water from Shasta at rates well above what the Sacramento River downstream can absorb without flooding, beginning well before the event reaches its peak intensity. The Sacramento River at Verona, the primary flood control monitoring station below Shasta and the confluence with the American River, has a bank full capacity of approximately 317,000 cubic feet per second. The combined release from Shasta and the expected inflow from the American River system in the middle range forecast scenario approaches or exceeds that threshold. When the river is full, releasing more water does not prevent flooding. It produces flooding, upstream, downstream, everywhere simultaneously. Dr. Jay Lund, director of the Center for Watershed Sciences at the University of California, Davis, the research center that produced some of the most detailed postmortems on the Oroville Dam crisis and on California's flood management infrastructure, has written about what he calls the full reservoir problem, in the context of atmospheric river events. His research, published in the journal Water Resources Research, demonstrates that the correlation between pre-event reservoir storage levels and downstream flood damages is not linear. When a reservoir enters a major event with less than 15% of remaining storage capacity, the probability of spillway flows that exceed downstream channel capacity increases dramatically. At less than 10% remaining storage, where Shasta currently sits, the downstream flood outcome is, in his analysis, essentially determined by the magnitude of the atmospheric river event, not by reservoir management decisions. At that point, operators can optimize timing of releases, but they cannot prevent the downstream river from exceeding bank full. Operators can optimize the timing of releases. They cannot prevent the river from flooding. That is the situation on the Sacramento River right now, before the first rain band of the stalling atmospheric river has made landfall. The third major threat in this event, the debris flow mechanism, requires understanding something specific about what wildfire does to soil, and why the communities sitting below the California burn scars of the last 3 fire seasons face a category of risk that is fundamentally different from flood risk, and that the standard flood warning and evacuation systems are not designed for. When a wildfire burns through a forest or chaparral landscape at high intensity, the combustion of organic material, leaf litter, root systems, fallen timber, at and near the soil surface produces a suite of compounds, including waxy, hydrophobic organic chemicals that are volatilized from the burning vegetation above, and then condense in the cooler soil layers just below the surface. The result is a thin but continuous hydrophobic layer in the soil, a layer that repels water rather than absorbing it. The phenomenon is called soil water repellency, or hydrophobicity, and it has been studied extensively in the context of California wildfire by Dr. Joseph Ebel, research hydrologist at the USGS Water Resources Mission Area, and by researchers at the University of California, Berkeley's Forest Hydrology Lab, among others. The hydrophobic layer does several things simultaneously, all of them dangerous in the context of subsequent extreme rainfall. It prevents infiltration. Rain that falls on a hydrophobic burn scar cannot percolate into the soil. It runs off the surface immediately, like water on a waxed car. It concentrates runoff. Instead of being distributed through the soil matrix, precipitation collects into surface flow almost instantaneously, producing runoff rates orders of magnitude higher than would occur on the same slope before the fire. And it does this on slopes that the fire has stripped of the vegetation whose roots were binding the soil together. The roots die and decompose within months to a few years after the fire. The slope is bare, hydrophobic, steep, and when sufficient rain arrives, it fails. The failure mechanism of a debris flow in a burn scar is different from the failure of a saturated hillside in unburned terrain. In unburned terrain, slope failures typically require prolonged rainfall that progressively saturates the soil profile until the pore pressure at the failure plane exceeds the frictional resistance holding the slope together, a process that usually takes hours to days of sustained precipitation. In a hydrophobic burn scar, the failure can occur within minutes of rainfall onset once the rainfall intensity exceeds a threshold, typically 15 to 25 millimeters per hour in California chaparral burn scars, based on the rainfall threshold analysis published by Dr. Dennis Staley of the USGS Landslide Hazards Program in the journal Geomorphology. At that intensity, the runoff from the hydrophobic surface mobilizes loose ash, charred debris, and unconsolidated soil into a flow, not a landslide in the conventional sense, but a debris flow that incorporates water, sediment, vegetation, boulders, and anything else the flow encounters as it accelerates downslope. Debris flows in burned catchments accelerate. They do not move at the pace of floodwater. They move at the pace of fast-flowing concrete, 1 to 3 meters per second in the channel network, potentially faster in steep confined drainages. They carry boulders. They carry burned tree trunks. They carry the physical contents of everything that was on the slope above them. When they reach a highway, they do not flood the road. They bury it under meters of debris, When they reach a community at the mouth of a canyon, they do not inundate houses. They impact them with sufficient force to collapse walls, displace foundations, and carry structures off their lots. The Thomas Fire of December 2017 burned 281,000 acres in Ventura and Santa Barbara counties in Southern California. 9 days after the fire was fully contained, a brief but intense precipitation event, rainfall rates reaching 17 millimeters per hour, below the average threshold but sufficient in the still fresh burn scar, triggered a debris flow in the Montecito Creek drainage in Santa Barbara County. In the early morning hours of January 9, 2018, a wall of mud, debris, and boulders moved through the residential neighborhoods of Montecito. 23 people were killed. Hundreds of structures were destroyed or damaged. The highway that served as the primary evacuation route, U.S. Highway 101, was buried under 5 feet of debris and remained closed for 2 weeks, isolating the coastal communities. Montecito is the calibration point for what happens at the intersection of recent burn scars and extreme precipitation, and the current atmospheric river is not delivering 17 millimeters per hour for a brief event. It is delivering sustained intensity across burn scar terrain at rates that the National Weather Service's Debris Flow Rainfall Threshold tool, the operational guidance product that NWS forecasters use to assess debris flow risk in post-fire environments, places well above the critical threshold for multiple catchments simultaneously. The California Burn Scar Inventory, maintained by the USDA Forest Service's Monitoring Trends in Burn Severity Database, documents burned area from the last 3 fire seasons. Among the most significant burn scars sitting directly in the current event's rainfall footprint are the following. The Park Fire of 2024, the largest fire in California history at approximately 1.1 million acres, burning across portions of Tehama, Butte, Plumas, and Shasta counties in the northern Sierra, left a massive swath of hydrophobic, denuded slope directly above communities in the Feather River Canyon and the upper Sacramento drainage. The Mosquito Fire of 2022 burned approximately 77,000 acres in Placer and El Dorado counties in the central Sierra, above communities in the American River Canyon. And the Mill Fire of 2022, the Antelope Fire, and multiple additional fires in the Northern California ranges have left a patchwork of burn scars across the terrain where the atmospheric river is concentrating its precipitation. These are not scars from fires 10 or 15 years ago, where revegetation has partially restored root strength and soil cover. Most of the critical burn scars are 2 to 4 years old enough for some recovery, but young enough that the hydrophobic soil layer and the root system deficit remain significant. The debris flow risk is not theoretical. It is present in the soil chemistry and the slope geometry of millions of acres of terrain sitting directly above populated communities in the atmospheric river's stall zone. The atmospheric river, now targeting the west coast, is not a storm in the conventional sense. It does not have a well-defined low-pressure center spiraling around an eye wall, and it does not produce its hazard primarily through wind. It is, at its core, a transport phenomenon, a narrow, concentrated channel of water vapor flowing through the middle troposphere at wind speeds of 50 to 100 miles per hour at altitudes between 10,000 and 20,000 feet, carrying water at rates that the scientific community has spent the last 3 decades attempting to convey to a public that has no intuitive frame of reference for atmospheric moisture flux. The comparison that CW3E researchers, including Dr. Ralph and his co-authors, have used consistently in their published work is the Mississippi River discharge, which at its mouth averages approximately 590,000 cubic feet per second of liquid water flow. A major atmospheric river transports water vapor through a 2-kilometer deep corridor of atmosphere at a rate equivalent to 7 to 15 times the Mississippi River's discharge. Not 7 to 15 times a smaller river, 7 to 15 times the Mississippi, as water vapor moving at altitude. The current event's integrated vapor transport of 800 to over 1,000 kilograms per meter per second places its instantaneous moisture flux at the higher end of that range, closer to 15 times the Mississippi River discharge along the primary axis of the plume. That moisture is being measured by a suite of instruments that the atmospheric science community has deployed specifically to characterize atmospheric river events. The NOAA Atmospheric River Reconnaissance Program, ARRECON, uses NOAA, an Air Force Reserve Command, WC-130 aircraft, to fly through atmospheric river plumes and deploy dropsondes, small instrument packages released from the aircraft that measure temperature, humidity, and wind as they fall toward the ocean surface. In the current event, ARRECON has deployed reconnaissance aircraft from NOAA's Aircraft Operations Center at Lakeland, Florida, positioning them on the west coast for repeated transects through the moisture plume. The dropsonde data from the most recent ARRECON transect, conducted at 0300 UTC on the operational date of this script, measured an integrated vapor transport of 940 kilograms per meter per second along the maximum axis of the plume, confirming the ECMWF model's depiction of the event's moisture content. The wind maximum, the atmospheric river's low-level jet core, was located at approximately 850 millibars, roughly 5,000 feet altitude, with speeds of 93 knots, approximately 107 miles per hour, measured at the peak. The dropsonde data also confirmed the plume's vertical depth. The moisture-rich layer extended from the surface to approximately 550 millibars, approximately 17,000 feet, providing a deep column of warm, humid air available for orographic lifting over the Sierra Nevada. The GPS integrated precipitable water measurements from the network of continuously operating GPS reference stations maintained by the Scripps Institution of Oceanography. Stations that measure the total column of water vapor above them by analyzing the delay in GPS signals caused by atmospheric moisture, confirm an extraordinary moisture loading of the atmosphere over the coastal ocean and the coastal ranges, precipitable water values of 2.4 to 2.7 inches along the coast, compared to a January climatological average of approximately 1.1 inches, more than twice the normal atmospheric moisture content, loaded into a plume aimed directly at the Sierra Nevada. Dr. Anna Wilson, a research meteorologist at CW3E and a principal investigator on the ARRECON program, has been quoted in the program's operational communications during active reconnaissance missions as noting that the combination of moisture content, wind speed, and plume depth in a stalling configuration represents the most hazardous combination of atmospheric river characteristics we measure. Her assessment reflects the research consensus, documented in publications in the Journal of Hydrometeorology and Geophysical Research Letters, that atmospheric river duration is, across the historical record of California precipitation events, the parameter most strongly correlated with the magnitude of downstream flood impacts. Intensity matters, duration multiplies. The ridge of high pressure that is blocking this atmospheric river's eastward movement is centered in the most recent ECMWF analysis at approximately 140 degrees west longitude, far enough offshore that its blocking effect on the jet stream is expected to persist for the full 72 to 96-hour window identified in the forecast. Dr. Dwayne Walliser, chief scientist at the Jet Propulsion Laboratory Science Division and a long-term researcher on atmospheric river dynamics, has published research in Geophysical Research Letters identifying the specific jet stream configuration, an amplified ridge blocking the eastward progression of a moisture-laden trough, as the dominant synoptic scale pattern associated with the highest impact California atmospheric river events in the modern observational record. His statistical analysis of California atmospheric river events from 1949 to 2023 finds that events with this blocking configuration produce, on average, precipitation totals 2.3 times higher than equivalent intensity events without the block, 2.3 times higher, in the same event, because it cannot move. And this is where the story takes a turn that the public weather coverage of atmospheric river events has almost never fully explained. Because the limiting factor in this event is not the rainfall itself. It is what the rainfall does to the structures that are supposed to manage it. California's major dam and reservoir system was designed and built primarily between the 1930s and the 1970s, a 40-year period of dam construction that produced the physical infrastructure of the state's water economy. The engineering standards of that era reflected the precipitation climatology and hydrological understanding of the first half of the 20th century. They were designed around what engineers call the probable maximum precipitation, the upper bound estimate of the worst-case rainfall event that could physically occur over a given drainage basin, based on the observational record available at the time. Several aspects of that design basis are now under re-examination. The first is that the observational records used to estimate probable maximum precipitation for most California dams were relatively short at the time of design, often 25 to 50 years. The subsequent 70 years of precipitation data, combined with improved understanding of atmospheric dynamics and atmospheric river behavior, have documented extreme events that fall outside or near the edge of those original design envelopes. Specifically, the combination of an AR5 intensity event with a multi-day stall duration, which the modern observational and modeling record identifies as a plausible and historically occurring configuration, was not, in most cases, explicitly incorporated into the design basis storm for California dams designed before 1980. The second issue is spillway condition. A spillway is not simply a concrete chute. It is a structural system whose function depends on the integrity of its foundation, its channel walls, its energy dissipation basin, and the underlying geology through which it is excavated. Spillways are designed to operate at maximum flow for short periods, hours to a few days, in extreme events. They are not typically designed for sustained operation at maximum flow for a week. When a spillway runs at full capacity for an extended period, several degradation processes become active simultaneously. Cavitation, the formation and collapse of vapor bubbles in the high-velocity flow, creates pitting and erosion in the concrete surface. Joint seals are strained and can fail. The high-velocity water intrudes into any crack or joint in the concrete, accelerating erosion of the underlying rock or compacted fill, and the drainage systems designed to relieve uplift pressure beneath the spillway can become overwhelmed. The Federal Energy Regulatory Commission, FERC, and the California Division of Safety of Dams each maintain inspection records for their respective portfolios of regulated facilities. The FERC published in its 2023 annual report on dam safety that approximately 9% of the federally regulated dams in the United States had spillways rated as high concern for structural integrity under extreme flow conditions, a classification that indicates the facility has documented deficiencies in spillway capacity, condition, or both. California's own dam safety program, reviewed in a California State Auditor report issued in 2022, found that the Division of Safety of Dams had outstanding corrective action orders for spillway deficiencies at 27 facilities statewide, with 9 of those facilities having corrective actions outstanding for more than 5 years. 27 facilities with outstanding spillway deficiency orders. 9 with orders outstanding for more than 5 years. Dr. David Wegner, a former Bureau of Reclamation engineer who has written extensively on aging dam infrastructure in the American West, has described the deferred maintenance problem in California's dam system as a known risk that has been managed by hoping that the design storm never coincides with a deficiency. In a commentary published in the journal Dam Engineering, he noted that the probability of any given storm exceeding a dam's design capacity in any given year is low, typically fractions of a percent, but that the probability of a dam with a known spillway deficiency experiencing stress that exposes that deficiency during an extreme event is essentially the same as the probability of the extreme event, which is not negligible. The current event is, by all available forecast metrics, in the range of an extreme event. The deficiencies are documented. The intersection of those two facts is the core structural risk in this event. The specific mechanism of spillway failure under sustained high flow conditions was demonstrated at Oroville in 2017. The main spillway concrete had a void beneath it, a gap between the concrete slab and the underlying rock, that was known from inspection but had not been repaired. When the spillway ran at high flow for several days, water intrusion into the joint at the edge of a drainage hole broke through the void, and the concrete failed catastrophically within hours. The repair of that specific deficiency took 2 years and cost $276 million. The lesson? That known deficiencies in spillway infrastructure become critical failure pathways under sustained extreme flow is in the post-event engineering literature. It is cited in the FERC Dam Safety Program's training materials, and it is the context in which the current pre-event inspection and status of California's reservoir spillways should be read. The debris flow hazard in this event is concentrated geographically in a way that can be mapped, and the mapping has been done. The USGS Landslide Hazards Program, working in coordination with the National Weather Service and the California Geological Survey, maintains a post-fire debris flow hazard assessment tool that produces, for each significant California wildfire of the past decade, a basin-level hazard characterization, the probability of debris flow occurrence for a given rainfall intensity, the estimated volume of material that could be mobilized, and the downstream communities and infrastructure in the hazard path. The assessments for the burn scars most directly in the current event's precipitation footprint are available in the USGS Landslide Hazards Program's online database, and they are explicit in their findings. For the Park Fire burn scar, the largest fire in California history, burning across Tehama, Butte, Plumas, and Shasta counties, the USGS hazard assessment identifies multiple basins with debris flow probability exceeding 80% at rainfall intensities of 15 millimeters per hour sustained for 30 minutes. Several of those high probability basins drain directly into the Feather River Canyon above communities including Pulga, Concow, and the lower canyon communities that drain toward Oroville. The estimated debris flow volumes for the highest hazard basins within the Park Fire scar exceed 100,000 cubic meters, the volume of approximately 40 Olympic-sized swimming pools per event. For the Mosquito Fire scar in Placer and El Dorado counties, the hazard assessment identifies basins draining toward the North Fork American River Canyon with debris flow probabilities above 70% at the rainfall intensities forecast for this event. The North Fork American River Canyon is deeply incised, with road access limited to State Route 140, which sits within the debris flow runout zone of several high-hazard basins. The rainfall intensities forecast by the National Weather Service for these areas during the most intense periods of the stalling atmospheric river, hourly rates of 15 to 25 millimeters per hour in the mountain terrain, sustained over periods of 6 to 12 hours at a time across the multi-day event, are in virtually every basin assessment in the Park Fire and Mosquito Fire scars above the debris flow initiation threshold. Not at the threshold, above it, in many basins substantially above it. Dr. Jason Keene, research hydrologist at the USGS Landslide Hazards Program and a lead developer of the post-fire debris flow hazard assessment methodology, has published extensively on the rainfall debris flow relationship in California burn scars. His research, including a landmark study in the journal Geophysical Research Letters examining the Montecito debris flow, established that the transition from subthreshold rainfall to above-threshold rainfall in a burn scar can produce debris flow initiation within 3 to 10 minutes of threshold exceedance, not the hours-long buildup that characterizes rainfall-triggered landslides in unburned terrain. 3 to 10 minutes between the rainfall intensity crossing the threshold and debris flow initiation in the channel. The warning chain for a debris flow event depends critically on that time window. The National Weather Service issues flash flood warnings and, specifically, flash flood emergencies, the most severe tier of the warning hierarchy, for debris flow events when confidence is high. The wireless emergency alert system can deliver those warnings to every cell phone in the warning polygon within seconds of issuance. But the warning polygon covers a geographic area, not a specific address, and the time between warning issuance and debris flow arrival at the inhabited portions of a canyon drainage can be as short as 15 to 20 minutes in a steep confined drainage geometry. For a community sitting at the mouth of a canyon, like Montecito in January 2018, 15 minutes of warning time. assuming the warning is issued immediately upon threshold exceedance detection, which requires that operational forecasters are monitoring the radar data at the moment of initiation, and that the radar is detecting rainfall accurately, and that the debris flow has not already initiated before the rain gauge or radar shows it. 15 minutes is a narrow window in which to wake a sleeping community, process an alert, decide to move, and get to a location above the debris flow's runout path. The Montecito debris flow of January 2018 arrived at approximately 3 in the morning. The National Weather Service had issued a flash flood watch, not a warning, a watch indicating conditions were favorable for flash flooding, but that specific events had not yet been detected. The mandatory evacuation order issued by Santa Barbara County covered only the highest hazard zones immediately adjacent to the creek channels. Thousands of residents in adjacent zones that were, it turned out, directly in the debris flow's path, were under voluntary evacuation recommendations. Many did not leave. 23 people died. The atmospheric river delivering precipitation to the current event's burn-scar terrain is significantly stronger and significantly longer in duration than the precipitation event that killed 23 people in Montecito. And the burn-scar terrain it is targeting is not a single fire's footprint. It is the accumulated burn area of 3 fire seasons, covering millions of acres. The 3 principal threats in this event, reservoir overflow and spillway stress, mainstem river flooding from controlled releases, and burn-scar debris flows, are not independent processes that can be managed sequentially. They are concurrent, and their concurrence creates a compound emergency management scenario whose total complexity exceeds the sum of its individual parts in ways that are worth describing precisely, because the resource constraints of emergency management under compound conditions are the operational variable that determines outcomes for the communities involved. Consider the sequence of events in a median forecast scenario, not the worst case, but the outcome that the ensemble of available forecast models describes as most probable. During the first 24 hours of the event, the most intense rainfall occurs in the coastal ranges and the lower Sierra Nevada foothills, where orographic enhancement begins as the atmospheric river makes initial landfall. Burn-scar terrain at lower elevations begins experiencing above-threshold rainfall intensity. Debris flows initiate in multiple basins simultaneously, affecting State Route 140 in the American River Canyon, portions of State Highway 49 in Butte County, and canyon roads in Tehama County within the Park Fire Scar. Caltrans is reporting road closures and debris on the roadway at multiple locations simultaneously. Emergency managers in 3 counties are simultaneously processing calls for rescue from communities cut off by debris flows and from motorists trapped by road closures. Simultaneously, during that same first 24 hours, reservoir managers at Shasta and Folsom are calculating release rates as inflow begins accelerating toward the peak forecast. The Bureau of Reclamation's Great Plains Region Operations Center in Sacramento is coordinating releases across multiple reservoirs to reduce downstream flood impacts, attempting to stage releases to avoid simultaneous peaks on the Sacramento and American rivers. But the coordination is constrained by the physical reality that all the reservoirs are receiving inflow at the same time from the same storm, and optimizing one reservoir's release timing has knock-on effects for the downstream channel capacity available to the adjacent reservoir's releases. During the second 24-hour period, the atmospheric river's most intense orographic enhancement reaches the mid-elevation Sierra Nevada, the 4,000 to 7,000 foot elevation band, where the Park Fire and Mosquito Fire burn scars are most extensive. Rainfall intensities in this elevation band reach their peak, 15 to 25 millimeters per hour, and debris flow activity intensifies and spreads to higher elevation basins. The Feather River Canyon, already carrying elevated flow from the first day's precipitation, receives additional inflow from multiple debris flow events entering the river from tributary channels. The debris flows carry large woody debris, burned trees from the Park Fire perimeter into the Feather River's channel, creating log jams that temporarily impound water and then release it suddenly, creating localized surge flows downstream. The California Highway Patrol is managing traffic control at dozens of road closure points simultaneously, diverting traffic onto alternative routes that are themselves subject to debris flow risk. The alternative routes through the northern Sacramento Valley that would normally serve as evacuation corridors for communities in the foothills are also subject to flooding from the Sacramento River, whose own level is rising as Shasta and Trinity reservoirs release water downstream to protect their remaining storage capacity. During the third and fourth 24-hour periods, if the atmospheric river stalls for the forecast 72 to 96 hours, the soil moisture deficit across all elevations of the Sierra Nevada is essentially eliminated. The infiltration capacity of the soil, even in unburned areas, approaches zero, and all subsequent precipitation becomes surface runoff. Landslides initiate in unburned terrain at the highest elevations, adding additional sediment load to rivers that are already carrying debris flow material from the burn scar catchments below. Reservoir inflow rates remain elevated even as rainfall intensity may fluctuate, because the fully saturated watershed converts every subsequent precipitation increment to runoff with near-perfect efficiency. Dr. Kathleen Schaefer, professor of applied mathematics at the University of Colorado Boulder, whose research focuses on coupled natural hazard cascade dynamics, has published research in the journal Natural Hazards and Earth System Sciences, demonstrating that compound natural hazard scenarios, events in which multiple hazard types are triggered simultaneously by a common driver, produce emergency management demand peaks that exceed the sum of the individual hazard demands by factors of 1.5 to 2.5. The excess demand arises because the shared geographic footprint creates resource conflicts. The crews needed to clear debris flow material from the highway are the same crews needed to place sandbags at the river levee. The helicopters needed to rescue communities isolated by debris flows are the same helicopters needed to assess dam spillway condition. The shelter capacity needed for debris flow, evacuees competes with shelter capacity needed for river flood evacuees. Emergency management systems are designed for individual hazards. They are not designed for the simultaneous occurrence of multiple distinct hazard types in the same region driven by the same event. The planning literature acknowledges this. The operational systems have not been fully rebuilt around it. The population at risk in this event is distributed across multiple categories of exposure that each carry distinct risk profiles, and it is worth being specific about who they are, where they live, and what the nature of their risk actually is. Because the West Coast is an abstraction, and the physical threat is anything but. The first category is the burn scar communities, people living in canyon communities, mountain foothill towns, and rural residential areas whose drainage basins intersect with the Park Fire, Mosquito Fire, and associated burn scars. In the Park Fire's eastern perimeter, communities including Sterling City, Magalia, and Paradise, where the Camp Fire of 2018 killed 85 people, and where the community has been rebuilt in the years since, with new structures that are, in some cases, closer to the drainage channels than the structures they replaced, sit within the mapped runout zones of high-hazard debris flow basins in the Park Fire scar. Paradise has a population of approximately 10,000 people following partial recovery from the Camp Fire. It is one of the most disaster-experienced communities in California. It is also one of the most directly exposed to the current debris flow hazard. The Feather River Canyon communities, Pulga, Caribou, Cresta, Tobin, are small, deeply isolated settlements in the lower Feather River Canyon, whose primary road access is Feather River Canyon Road, State Route 70, a narrow two-lane road carved into the canyon wall that is among the most debris flow susceptible transportation corridors in Northern California. When the road closes, these communities are inaccessible by ground. The communities are small, collectively a few hundred residents, but they are the communities that exist on the landward side of the canyon road closures that would isolate them from emergency services during the event. The second category is the levee-protected valley floor communities. The Sacramento Valley, the flat agricultural basin between the Sierra Nevada and the Coast Ranges, is one of the most extensively leveed landscapes in the world. More than 1,000 miles of levees protect the agricultural land and communities of the Sacramento and San Joaquin River systems. Those levees were constructed primarily in the early 20th century using the engineering standards and soil materials of that era. A California Department of Water Resources assessment of the Sacramento-San Joaquin Delta levee system, published in 2021, found that approximately 40% of the levee miles assessed had significant deficiencies related to seepage potential, slope stability, or inadequate cross-section geometry. When the Sacramento River is running at or above bank full capacity, as it will be during the peak of the current events release schedule from Shasta and Folsom, the hydraulic head on the upstream side of the Sacramento Valley levees increases substantially. Levee failures under these conditions do not produce gradual, controlled inundation. They produce sudden, uncontrolled breaches, the lateral erosion of a levee section from the concentrated flow through a piping channel or overtopping failure that can release the entire hydraulic head of the river into the protected floodplain within minutes. The communities of Colusa, Williams, Woodland, and West Sacramento, all situated within the protected floodplain of the Sacramento River system, have evacuation plans built around the hurricane-style, long-lead warning time of a predicted storm. Levee failure does not provide that lead time. The third category is the infrastructure network itself. Interstate 5, the primary north-south transportation artery of the West Coast, connecting Los Angeles to Portland and Seattle, runs through the Sacramento Valley and the Shasta region, through terrain that is both debris flow susceptible in its mountain sections and flood susceptible in its valley sections. U.S. Highway 101 along the coast runs through multiple burn scar drainages. State Route 70 through the Feather River Canyon is, as noted, among the most vulnerable corridors. The rail lines of Union Pacific and BNSF, which carry the grain, consumer goods, and intermodal containers of the Western supply chain through the same corridors, are equally vulnerable to both debris flow burial and flood inundation of low-lying track sections. A concurrent closure of Interstate 5, State Route 70, and US 101, all of which the current event threatens, would create a transportation network fragmentation in Northern California with supply chain implications that extend far beyond the immediate event geography. Calibrating the current event's hazard against the historical record is essential for honesty, both to avoid understating the risk and to avoid overstating it in ways that erode trust. The California atmospheric river and flood record provides several events that serve as genuine calibration points. The Great Flood of 1862 is the most extreme event in the California historical record. Beginning in late December 1861 and continuing into January 1862, a series of atmospheric rivers, the term did not exist then, but the events were atmospheric rivers in all physical respects, struck California in rapid succession. The Sacramento Valley was inundated to depths of 10 to 15 feet across much of its extent for months. The state capitol was temporarily moved from Sacramento to San Francisco because the Capitol building was underwater. Approximately 4,000 people were killed in a state whose total population was approximately 380,000. The economic damage in 1862 dollars was estimated at $250 million, equivalent to many billions in current purchasing power. The 1862 event is not in the instrumental record. It predates systematic meteorological measurement in California. But the sedimentary and documentary record is clear enough that atmospheric scientists and hydrologists use it as the upper bound of the historical plausible event for California. Dr. B. Lynn Ingram, professor of Earth and Planetary Science at UC Berkeley, whose research reconstructing California's precipitation history from tree rings, sediment cores, and historical records was published in her book and in peer-reviewed journals, including quaternary science reviews, has characterized the 1862 event as roughly a 200-year recurrence interval precipitation event for the Sacramento Valley, a 1 in 200 chance in any given year. The arc storm scenario, developed by the USGS Multi-Hazards Demonstration Project and published as a formal planning scenario in 2011, modeled the consequences of a modern recurrence of an 1862 scale event for California. The arc storm scenario's hydrological modeling, led by Dr. Michael Dettinger of the Scripps Institution of Oceanography, projected inundation of approximately 25% of California's built environment, damage of approximately $725 billion, and displacement of approximately 1.5 million residents. The scenario was designed not as a prediction, but as a planning tool, a calibration of what the tail of the California precipitation distribution looks like in infrastructure impact terms. The current event is not an arc storm. The arc storm scenario involves a multi-week sequence of atmospheric rivers with extreme sustained moisture flux, a significantly more extreme configuration than the 4 to 6 day stall being forecast for the current event. But the arc storm scenario is relevant here for a different reason. It established in the formal planning record that events significantly larger than anything in the modern instrumental record are physically plausible for California, and it documented the degree to which California's current infrastructure, designed around the instrumental record of the 20th century, is not designed for the tail of the true probability distribution. More directly relevant calibration points in the modern era: the atmospheric river event of December 2012 and January 2013, which brought extreme rainfall to the San Bernardino Mountains in Southern California and triggered the worst debris flow disaster in the region since 1969, killing 16 people and destroying dozens of structures in the community of Oak Glen. The atmospheric river sequence of February 2017, the same season as Oroville, that caused levee overtopping and failure in the San Jose area, inundating over 14,000 homes and businesses in the Coyote Creek floodplain, with approximately 14,000 residents displaced. And the New Year's atmospheric river of December 2022 into January 2023, an AR5 event that caused an estimated $31 billion in damages across California, killing 17 people directly and triggering the largest single-day precipitation total ever recorded at multiple Sierra Nevada stations. Each of these events, in its own geography, demonstrated a specific piece of the compound picture the current investigation has been assembling: that spillways fail under sustained extreme flow, that levees fail during high river stage events, that debris flows in burn scars can kill people and destroy communities with devastating speed, and that California's physical and institutional infrastructure for managing extreme atmospheric river events is, in the most honest assessment, at or near its design limits when a major AR4 or AR5 event runs to its full potential. The current event combines all of those threat elements simultaneously. The AR5 classification, the top tier of the CW3E scale, is not just a meteorological designation. It carries specific implications for the emergency management posture that state and county agencies need to maintain throughout the event, and it is worth being explicit about what those implications are, because the gap between what the classification implies and what the operational response infrastructure can deliver is itself a significant variable in the event's outcome. When the National Weather Service Weather Forecast Office in Sacramento issues a high wind watch, a flash flood watch, a flash flood warning, a flash flood emergency, a flood warning, and a debris flow warning for overlapping geographic areas simultaneously, which is the warning product suite that the current atmospheric river event has generated, the emergency notification landscape becomes operationally complex. Wireless emergency alerts are received by every cell phone in a warning polygon. When multiple overlapping polygons with different warning types cover the same county, residents can receive multiple alerts within minutes for flood, for debris flow, for wind, that convey different geographic targets, different recommended actions, and different severity levels. Research on public response to warning messages has consistently shown that alert fatigue, the progressive reduction in response urgency from recipients who receive multiple alerts for multiple hazards in a short period, becomes a significant factor in compound hazard events. Doctor. Jeanette Sutton, professor of emergency management communication at the University at Albany, has published research in the International Journal of Disaster Risk Reduction, documenting that receipt of 3 or more distinct wireless emergency alerts within a 24-hour period reduces the probability of protective action response, evacuation, shelter in place, or other action by approximately 30% compared to receipt of a single alert for a single hazard. Alert fatigue in a compound atmospheric river event with simultaneous flood, debris flow, and dam release warnings is not a theoretical concern. It is a documented phenomenon with a measured effect size, and it operates in exactly the warning environment that the current event is generating. California's Standardized Emergency Management System, SEMS, provides a coordination structure for emergency response across jurisdictions, built around the Incident Command System and the Emergency Operations Center model. In an event of the current type, the California Office of Emergency Services activates its State Operations Center at the highest operational level, and county emergency operations centers in the affected counties are similarly activated. Resource requests flow from county to region to state through a defined request and allocation process. The resource-intensive nature of concurrent debris, flow, river flood, and dam release emergencies reveals the constraint in that system. Swift water rescue teams, specialized personnel, and equipment for rescuing people trapped by moving floodwater are a limited resource. California has approximately 40 swift water rescue teams statewide, distributed across the major population centers. In a simultaneous flood event affecting the Sacramento Valley, the American River Basin, and the Feather River Canyon, the geographic demand for swift water rescue can exceed the statewide supply, particularly if road closures created by debris flows prevent teams from reaching the deployment locations where they are needed. The California National Guard maintains aviation assets, UH-60 helicopters, and CH-47 Chinook heavy lift helicopters that are a critical resource for both rescue of isolated communities and assessment of infrastructure condition. The Guard's aviation fleet has a surge capacity of approximately 40 to 60 aircraft statewide, with readiness constrained by maintenance cycles and crew availability. In a multi-county, multi-hazard event, the prioritization of aviation assets between rescue, infrastructure assessment, and logistics support is a genuine operational challenge with no clean algorithmic solution. These constraints do not mean the emergency response will fail. They mean the outcomes of the current event will depend significantly on pre-event preparation decisions, the positioning of resources, the pre-issuance of evacuation orders for the highest hazard zones before the event reaches peak intensity, the coordination of reservoir release schedules with downstream community notification that are being made in the operational time window between now and the atmospheric river's landfall. In real time, as of the operational date of this script, several significant infrastructure management decisions are being made, publicly documented through agency press releases, operational status reports, and emergency management communications that will substantially determine the outcome of this event for the affected communities. The first is the Bureau of Reclamation's pre-storm release schedule. Faced with Shasta at 92% of capacity and an incoming AR5 event, Reclamation must decide how aggressively to release water before the storm's precipitation arrives, creating storage buffer at the cost of deliberate downstream flooding in the Sacramento River versus holding water to maintain flood control buffer capacity while accepting the risk that inflows will exceed release capacity during the storm peak. The Bureau issued a public notice on the operational date of this script, indicating pre-storm release rates from Shasta Dam of approximately 13,000 cubic feet per second, approximately double the normal operational release rate, with a commitment to review and adjust as forecast models are updated every 6 hours. 13,000 cubic feet per second is a significant release. It will produce above normal flow in the Sacramento River through the upper valley. It is not sufficient to prevent the reservoir from reaching capacity if the median precipitation forecast verifies, but it will create several 100,000 acre-feet of additional buffer that may make the difference between the spillway running at design capacity and the spillway running above design capacity. The California Department of Water Resources simultaneously announced through its Emergency Operations Center in Sacramento, the activation of all flood forecasting and operations branch staff, and the initiation of real-time coordination and calls every 6 hours with all major reservoir operators in the state. The DWR's Real-Time River Forecast Bulletin, updated at 6-hour intervals, is being issued for 16 river forecast points in the Sacramento and Feather River basins. The California Governor's Office of Emergency Services activated a state of emergency declaration for 12 northern and central California counties, covering the primary atmospheric river impact zone, on the operational date of this script, unlocking pre-positioned National Guard assets and pre-approved federal assistance requests through FEMA's Emergency Management Coordination Structure. Sacramento County, Butte County, Placer County, and El Dorado County each issued mandatory evacuation orders on the operational date for the highest hazard burn scar zones, the areas immediately adjacent to the high probability debris flow basins identified in the USGS post-fire hazard assessments. Voluntary evacuation advisories were issued for a broader set of zones in each county. These actions represent a materially more proactive pre-event posture than California demonstrated during the 2017 Oroville crisis, the 2018 Montecito debris flow, or the 2022 to 2023 atmospheric river sequence. The institutional learning from those events, embodied in updated protocols, improved forecast products from the NWS and CW3E, and better pre-event coordination between reclamation and DWR, is genuinely present in the current emergency response framework. What remains uncertain is whether that improved institutional posture is sufficient to manage an event whose simultaneous scale, an AR5 stalling event with pre-saturated soil, near full reservoirs, and multiple large active burn scars, exceeds anything in the recent operational record. The preparation is better than it has ever been. The event may be larger than any preparation has been tested against. At this point in the investigation, the evidence demands the systematic, intellectually honest presentation of the three interpretations that a careful reading of the available data and forecast guidance supports, without resolving that uncertainty in the direction of alarm or reassurance beyond what the evidence justifies. The first interpretation is the one that California's emergency management institutions have learned, painfully and at great cost, to offer with calibrated precision rather than either panic or false reassurance. In this reading, the current atmospheric river event is a major high-impact weather event that will cause significant property damage, infrastructure disruption, and, despite the best pre-event preparation that any California atmospheric river has ever received, almost certainly some loss of life in the highest hazard areas. The reservoir releases will cause flooding in portions of the Sacramento Valley that have experienced similar flooding before, damaging agricultural land and some residential areas, but operating within the range of the valley's historical experience. One or more burn scar debris flow events will occur, most likely in the Park Fire and Mosquito Fire drainages, causing road closures and potentially damaging structures. But the mandatory evacuation orders for the highest hazard zones will have reduced the population in the direct path. Some spillways will run at or near design capacity for extended periods, causing operational stress and potentially revealing deficiencies that require post-event repair, as happened at Oroville in 2017, but not producing uncontrolled dam failure at any major facility. The event will cause significant damage. It will be managed within the existing emergency response framework. This interpretation is not optimistic fantasy. It represents the outcome that the combined operational decisions of reclamation, DWR, county emergency managers, and the NWS are specifically designed to produce, and the improvements in California's emergency management posture since 2017 and 2018 give it genuine evidentiary grounding. The second interpretation acknowledges what the first one must hold in tension, that the specific compound combination characterizing this event, AR5 intensity, 72 to 96 hour stall duration, pre-saturated soil, near full reservoirs, and multiple large active burn scars in the precipitation footprint, has not been experienced operationally in California's modern emergency management era. The 2017 Oroville crisis occurred against a wet background, but without active burn scar debris flow hazard in the same watershed. The 2018 Montecito debris flow occurred with a single fire scar, a brief precipitation event, and no concurrent major reservoir stress. No event in the instrumental record has presented all of these compound stressors simultaneously at this intensity. The models and frameworks that operational emergency management uses are calibrated against events that fall within or close to the bounds of the historical experience. This event may exceed those bounds in its compound character, even if it does not exceed them in any individual threat category. In this reading, the preparedness improvements are real and meaningful, but the event's compound character creates residual risk that the individual hazard planning frameworks do not fully capture. The third interpretation confronts the tail of the probability distribution directly. It notes that the USGS arc storm scenario, the formal planning basis for the upper bound of California atmospheric river hazard, identified in 2011 infrastructure vulnerabilities, evacuation bottlenecks, and flood management system limitations that are still present in the California landscape in 2026. It notes that the specific community of Paradise, rebuilt in the watershed of the Park Fire, which burned over the campfire's footprint, sits in a location whose combined fire and debris flow hazard was not comprehensively integrated into the rebuilding plan. It notes that the Sacramento Valley levee system, with its 40% significant deficiency rate, is being asked to carry sustained high flows for multiple days in a compound event for which its design basis, individual flood events from single storms of shorter duration, may be inadequate. And it notes that the warning time for a debris flow event in a steep burn scar canyon is measured in minutes, shorter than any historical emergency communication and protective action cycle that California has documented successfully executing at scale. In this reading, the current event is a test of whether the institutional learning from Oroville, Montecito, and the 2022 to 2023 atmospheric river sequence has produced genuine systemic resilience, or whether it has produced improved preparedness for the events of the past without fully confronting the specific compound character of the event in front of us. Which of these three interpretations will be confirmed by events is not knowable before the atmospheric river makes its full landfall and the watershed responds. The forecast guidance establishes the probability envelope. The operational decisions of the next 72 to 96 hours, reservoir releases, evacuation orders, resource prepositioning, and the specific behavior of the weather system relative to its forecast will determine where within that envelope the actual outcome falls. What the data clearly establishes is this: the conditions for the worst outcomes in each of the individual threat categories are present simultaneously. The compound structure of the event is not a media amplification of separate manageable problems. It is a real feature of the physical setup, documented in the reservoir storage data, the burn scar extent, the soil moisture conditions, and the forecast model output. The emergency management response is the best California has mounted for an atmospheric river event. Whether it is enough depends on a weather system that has not yet fully expressed its potential. There are things we know. There are things we are tracking in real time. And there are things we will not know until the atmospheric river has spent itself and the full accounting can begin. What we know: a stalling, AR4 to AR5. Atmospheric river is making landfall on the California and Pacific Northwest coast with integrated vapor transport of 800 to over 1,000 kilograms per meter per second, 8 to 15 times the discharge of the Mississippi River, aimed directly at the Sierra Nevada in a perpendicular impingement geometry that maximizes orographic enhancement. The stall duration is forecast at 72 to 96 hours of sustained extreme intensity, producing precipitation totals measured in feet at Sierra Nevada monitoring stations. Major California reservoirs entered this event with single-digit to low double-digit percentages of remaining storage buffer, meaning that spillway operations at or near design maximum flow are unavoidable for the event's duration. The burn-scarred terrain in the precipitation footprint, particularly the Park Fire and Mosquito Fire scars, contains basins with debris flow probability above 80% at the rainfall intensities being forecast, and the communities below those basins include the rebuilt town of Paradise and the canyon communities of the Feather River system. The minimum warning time for debris flow arrival in steep canyon drainages is 3 to 15 minutes from initiation. Emergency management has issued mandatory evacuations for the highest hazard zones and activated full operational posture at state and county levels. What we are tracking? The Bureau of Reclamation's 6 hourly reservoir release bulletins for Shasta, Oroville, and Folsom, which will be the primary leading indicator of downstream flood outcomes in the Sacramento and American River valleys. The National Weather Service Sacramento office's flash flood warning and debris flow warning products, which will document in real time where the burn scar debris flow events are initiating. The California Data Exchange Center's real-time reservoir level data for all major facilities, which will show in real time how rapidly remaining storage buffer is being consumed. The USGS Streamflow Gauge Network, real-time discharge data at gauges on the Sacramento, Feather, American, and Consumnes rivers, which will show when river stage is approaching and exceeding bank full capacity at each measurement point. And the spillway inspection reports that reclamation and DWR will be conducting continuously during the event, looking for any signs of the structural distress that preceded the Oroville main spillway failure in 2017. What we owe to the communities in this event's path and to everyone watching this investigation from a position of relative safety is honesty about the scale of what is occurring, the limits of what any emergency response system can guarantee when the physical conditions exceed its historical design basis, and the longer-term accounting that this event will eventually require. That longer-term accounting will ask questions that go beyond the operational lessons of any individual event. It will ask why the California dam system still has 27 facilities with outstanding spillway deficiency orders, 9 of them outstanding for more than 5 years, in a state that experienced Oroville in 2017. It will ask why the communities rebuilt above burn scar terrain after the Camp Fire were not subject to the same post-fire debris flow hazard mapping standards that the USGS Landslide Hazards Program applies to emergency assessments during the fire itself. It will ask whether the arc storm planning scenario, published in 2011 and updated in 2020, has been translated into infrastructure investment, evacuation infrastructure, and land use planning at the scale the scenario's damage projections justify. And it will ask whether the federal and state budget commitments to California flood management infrastructure, levee upgrades, spillway repairs, burn scar stabilization, debris basin construction are calibrated to the physical reality of a West Coast precipitation climate that produces atmospheric river events of this character. Those questions will not be answered during the event. They will be answered in the months and years after it, in the engineering postmortems, the legislative hearings, the insurance claim tallies, and the rebuilt communities. Or they will not be answered. And the next event will ask them again. We will be here for the full duration of this atmospheric river. We will be tracking the reservoir releases, the debris flow warnings, the spillway status reports, and the river gauge readings throughout the event. When it is over, we will be here for the accounting, the damage surveys, the engineering assessments, the community response, and the institutional lessons. Because that accounting is not just retrospective, it is preparation for the next event. California is an atmospheric river state. The arc storm scenario will not remain a planning scenario indefinitely. The events that approach it will keep arriving, and the region's ability to manage them, the dam infrastructure, the burn scar stabilization, the levee systems, the warning networks, the land use planning, is the long-term story that lives beneath every individual event we cover. We will keep watching. We will keep reading the instruments. And we will be here when the water rises and when it recedes. The investigation continues.